In this video, we want to review some of the concepts from Chapter 6. So we're going to do a little bit of substitution and a little bit of separable differential equations. So let me remind you first that what we're looking for when we do a separable differential equation, because it won't always be with y's and x's, is we're looking for when the change in the square is directly related to the value of the square. So how the square is changing is based on what the value of the square actually is. So here, when we have dy dx is equal to y divided by x, you see that the change in y, right, dy, has to do with what the value of y is. So this is why it's separable. I'm going to start by multiplying both sides by dx. I'm going to divide both sides by y. So I got 1 over y dy equals 1 over x dx. So I've separated, right? Separate and then integrate. So we have the natural log of y equals the natural log of x plus c. Now remember, you can solve for the constant at any point once the constant appears. I'm doing two of these in this video. I'm going to solve this one right now for the constant. Okay, so I go up here and you see that we're told when y is equal to e, x is equal to 1. So I'm going to do that. I'm going to plug that in. The natural log of e equals the natural log of 1 plus c. Well, the natural log of e is 1. Natural log of 1 is 0. So the constant is equal to 1. So now let me just go up here. I've got the natural log of y is equal to the natural log of x plus 1. When I want to get rid of the natural log, because the steps are separate, integrate, and solve for y, I'm going to take e to both sides. E to the natural log of y is y. This becomes e, the right side, e to the natural log of x multiplied by e to the first. Remember, when we are adding in an exponent, that means we're multiplying the bases. Okay? And again, if you need to, think about why that is, remember something like x squared multiplied by x to the 7th is equal to x to the 9th. So when we were multiplying those bases, we added the exponents. So we're really just doing the opposite here. Well, e to the natural log of x is just x, and e to the first is just e. So I have y equals x multiplied by e. I usually like to have the coefficient come first, so just ex. This is it. So it's a linear function with a slope of e. All right, this example. Again, remember we're looking for d square over d triangle, and you've got a square on the other side. We have that here. Okay, we've got dr. We're looking for how r changes, and that's directly related to the value of r. So, first thing I'm going to do is multiply both sides by dm. Do that right up here. And I'm going to divide both sides by r. Now, I personally would not move constants, and the reason I wouldn't do that is because remember the last step is always solve for, in this case, r, but solve for that one side. So why move things to it that in the end you're going to have to move right back? And you'll get the same answer, but it's going to take more algebra at the end. So it's I think, worth just leaving everything on the right side. So we separated, now we integrate. So we've got the natural log of r equals m squared plus a constant. Now, in the previous example, I solved for the constant right here. In this example, as I said, I'm going to wait till the end. Okay? So I want to solve for r. So e to both sides. I've got r equals e to the m squared multiplied by e to the c. Now remember, e to the c, this is just another constant. So I could write this as r equals a constant multiplied by e to the m squared. All right, now let's solve for c. We're told that r is 5 when m is 0. So let's solve that. We're going to have 5 equals c e to the 0. Well, e to the 0 is 1, so we end up with just 5 equals the constant. So I'm going to come over here. R is equal to 5e to the m squared. And that's it. Now, one thing I just wanted to point out here, because I think it's kind of interesting to look at, is that if I found the derivative of r, the derivative of 5e to the m squared is 5e to the m squared multiplied by 2m because of chain rule. And if you go back up here to this original differential equation, it was 2rm. Well, notice that the derivative, according to this, is the original function. See, r is equal to 5em squared. It's just that multiplied by 2m. And up here we said the derivative, dr dm, was equal to r multiplied by 2m. So that's a way to verify that they really are, that we really did do everything correctly. Last, finding the definite integral and rewriting it with new bounds. Well, I often will point out that the best thing to look for with integrals is to know if you have to do substitution is products and quotients. If you had something like, if I just added this on the bottom, if you had an integral of something like x squared plus the square root of x minus 3 dx, like that, there's no product or anything in here. It's just each term we know how to do. We know that the integral, the antiderivative of that is 1/3 x squared. We know the antiderivative of that, because it's x to the 1/2, is 2/3 x to the 3/2, and then antiderivative of 3 is 3x, and we put a plus c. Substitution, what we look for are a product. We have that here. We have x squared multiplied by the cosine of x cubed. Now I'm going to make u equal to x cubed, and then du is equal to 3x squared dx. I'm going to divide both sides by 3, like that. And what you see now is that I'm going to be able to take out the 1/3, or the x squared and dx with a 1/3 du, and I'm just going to have, I'll put the 1/3 out front, the cosine of u du. And I took away the product. So now it's just a nice, easy antiderivative. All right, now, in terms of the bounds, this is the key right here. This was the key to our entire substitution, and it's the key to the bounds as well. The bounds were in terms of x. Dx tells us what the bounds, what axis they were in relation to. So the old bound was 0. We just plugged that in. 0 cubed is 0, so the new bound is also 0. This bound was pi over 4. So we plug that in. Pi over 4 cubed is ugly, but it is our new bound. I'm just going to write pi over 4 cubed. Okay. So the antiderivative of cosine is sine, so I end up with 1/3 the sine of u evaluated at pi over 4 cubed and 0. And you would evaluate this with your calculator. Pi over 4 is not a nice, pi over 4 cubed, excuse me, is not a nice number to plug into sine. I believe you get 0.155 as your answer. Okay, but then we were able to rewrite the bounds, so we didn't have to go back to x cubed. If instead we'd said it's 1/3 sine of x cubed, we would go back to the old bounds, pi over 4 and 0.